Good afternoon. Thanks for the introductions. And good afternoon, everyone. Welcome to my talk. My name is Teng, and today I will going to introduce my recent work, facilitating robust 60 gigs network deployment by sensing ambient reflectors. This is a joint work with my colleague Anfu Zhou and my advisor from Xinyu Zhang from the University of Wisconsin-Madison. Nowadays, there are many demanding wireless applications, such as mobile-to-screen video cast, wireless virtual reality, and laptop docking stations. They require wireless bandwidth multifold higher than existing Wi-Fi. And to meet this demand, the 60 GHz wireless technology has emerged as a promising venue. It centers at 60 GHz and spans over 14 GHz spectrum. And the latest AO2.11 AD standards that's running on 60 GHz is expected to deliver up to 7 Gbps bitrate. Despite the huge potentials, the 60 GHz networks face some challenge because it's extremely vulnerable to the propagation loss and the optical blockage, since it's running at the ultra-high center frequency. To overcome this limitation, 60 GHz radios currently adopt many element phase array antennas for directional transmission. The directional beams are electrically steerable, and this feature allows them to steer around the obstacle blockage using nearby reflectors. Depending on the reflectivity and directionality, however, will make the 60 GHz network performance sensitive to the AP deployment and environmental characteristics. To understand this, let's consider an example as illustrated in the following two figures. If we deploy the access point as in the right figure, it will be better than as in the left one because it creates more reflective path, and the network will be more robust to the human blockage. To verify these ideas, we set up a measurement study. We used two 60 GHz laptops equipped with trip-band radios. We randomly placed them over 16 different locations and measured the throughput brought by humans, normalized by the unblocked one. The right figure shows that compared to the 2.4 GHz links, the 60 GHz links is more sensitive to the placement. As we can see, the 24 GHz link only shows about 20% variation. However, for the 60 GHz links, the variation can be up to 5 times. And we found out the 60 radios can more easily detour the blockage if it close to a nearby reflector. So changing the environment is not always feasible, but we can change the AP placement. But the problem is, how can we find out a good spot? One approach is to use a blanket size array that try all possible locations. However, the search space is formidable owing to the numerous location combinations and the blockage pattern. So in this work, we try to propose a new system called EMI. So it can sense the environment from the 60 GHz radius eyes. And the sensing will model the major reflector in the environment by moving the radio over a few sampling locations. And this will avoid the blanket size array. The sensing result will be supplied to predict the link of arbitrary locations, which in turn help optimize the AP deployment. The core challenge in this idea is that 60 GHz radios can only measure RSS and phase. It cannot provide detailed sampling like the cameras in conventional environment mapping. And to overcome this challenge, we leverage the sparsity of the 60 GHz channel. So from the 60 GHz radius eyes, there are only a few dominant reflectors in the environment. They account for more than 95% of the total power that can be seen by a receiver. And they affect the average case network performance and are of most interest for the network planner. And our design memory wants as follows. So we will fix the transmitters and move the receiver over a few sampling locations where it can see the nearby reflector. And then we disentangled the line of sight path and multiple reflected paths. And then reconstruct the structures by tracing back the invisible propagation paths. And one main challenge in this step is how to disentangle different paths using the 60 GHz phase array antenna. So conventional digital array antennas can apply the Eigen Angle analysis to estimate the angle of arrival and angle of departure, or called the AOA and AOD. However, this approach does not apply to the 60 GHz phase array antenna because you use a set of weight, or called code book, that will sum individual signal stream from each antenna element and obfuscate them. To overcome this limitation, our idea is to receive the signal using different sets of weight and solve for the individual signal stream. So we can receive, for example, in here we have 4 elements phase array. We can receive the signals using 4 sets of different weights. And then by inverting the weight matrix, we can isolate the signal from each antenna element. But the key question here is, can we find a set of weight to form a weight matrix that's invertible? The answer is positive because the 60 GHz code design generally will ensure orthogonality between weights so as to maximize the spatial isolation across beam pattern. And this approach allows us to apply the conventional Eigen Angle analysis and to achieve a very high resolution in angle estimation. However, the above identified AOA and AOD do not have pairwise mapping. In other words, we don't know which AOA and AOD belong to the same path. To solve this problem, our idea is to process the received signal offline. Recall that we already recovered the individual signals from each antenna element so that we can process them offline. They can bypass the code constraint and virtually beamform to any direction. So our idea is to test each combination of AOA and AOD and choose the ones that give the strongest signal strength as a pair. We also generate the beam pattern that steers its side lobe away from those known signal direction so that we can isolate the signals along each path. And we can also estimate the path length for each path. So modern 60 GHz radio commonly adopts OFDM, which modulate the signals across different frequency tones. And to estimate the path length, it may leverage the phase divergence across OFDM tones. So as illustrated in this example, the phase of true frequency diverge over distance. And based on the phase differences among different frequency tones, we form an optimization that can map the delta phase back to the distance. So with the channel sensing information, we are able to locate the reflecting point by tracing back the AOA, AOD, and length of each path. So let's look at examples. If we have a single path, actually we cannot uniquely pinpoint the reflector because there's many other locations satisfying the same constraint. However, we can resolve this ambiguity by adding another path. And practical environment typically will encounter multiple paths, and we formulated this as a least square optimization that jointly consider them. And this model only considers the first order reflection from the reflector. And higher order reflections do not follow this model. But we can easily filter them out because they tend to show a larger deviations in the models. And with the reflecting point, IMI will create a 2D cross-section of the environment. And in here, we abstract the reflector as two kinds, specular reflector and diffusive reflector. The former is for the large continuous surface that like the walls, and the latter is for the small size objects like the pillar and computer case. And specular reflector will model the reflections like a mirror, and it reflects the signals look like emitting from the virtual source. And the diffusive reflectors will scatter the signals toward a wide range of angle. Besides, IMI can also estimate the reflectivity of each reflector, or the reflection loss of each reflector. Note that the received signals of each path is determined by multiple factors, but not all of them are known by the radios. And we address this problem by using the line of sight path as a reference calibration to cancel those unknown factors. To predict the link of arbitrary locations, IMI employ a 60 Hz parametric retracing engine. So ray tracing has been demonstrated by previous 60 Hz measurement study as a fine-grained way to model the 60 Hz signals. So it recursively traces the signal propagations, and it will capture the attenuation and reflection effects. So the parametric ray tracing engine will take the layout and reflectivity for the dominant reflector as input and predict the RSS at the receiver side. So with the link prediction capability, IMI will be applied to optimize the network deployment. So in here, we focus on an example case study that targets to maximize the network coverage using multiple access points. However, IMI can also be applied to other optimizations, and they will follow a similar procedure. Our basic idea is to predict the AP location for a given set of client spots. The prediction will take the reconstruct environment as input. And we also need to define a performance metric. For example, here, we are interested in maximizing the average bit rate among all client spots. With these two, IMI will predict the performance of all candidate AP locations, and we will take the one that maximizes the performance metrics as output. And we implement a version of IMI using a custom-built 60 Hz software-defined radio testbed. And since the programmable many-element phase array antenna is still not yet commercially available, we reproduce its end effect using a moving antenna. To do that, we mount omnidirectional antennas onto a programmable motion control system and synthesize the signals of a 16-element circular array. And we conduct the experiment in an office environment. And the dominant reflector in these rooms are mainly the concrete wall, drywall, and the pillar inside the room. To evaluate the effectiveness of the environment sensing, we first collect the trace data, and then we also measure the ground truth by using another pair of radios that equipped with the horn antenna and steer its narrow beams at the step of 3 degrees. And the left figure shows the accuracy of the estimate AOA and AOD. So the average error is less than 5 degrees. And the error is much smaller than the couple-based beam scanning method that equivalent to you try each possible beam direction. And the right figure shows the estimate path length. And the average error is about 0.3 meters. And we found the line of sight paths tend to have better accuracy than the non-line of sight paths because it tends to have better signal strength. To evaluate the environment reconstruction, We move the radio over 15 uniform locations to sense the dominant reflectors. And the following figure shows the resulting reconstruction. So we dim the reflector as a mirror and find out its virtual source, and then recover the specular reflector positions. And in a similar way, we recover the specular, the diffusive reflector location. And the color line in the right figure shows the position of the wall and also the position of diffusive reflectors. And they well match with the ground truth. And to evaluate the accuracy of link performance prediction, we predict the spatial channel profile for another set of randomly 15 randomly located TSIS pair. And the top figure shows the predict angle difference and the ISS difference. So there are average error about 5 degrees and 3 dB. So in here, the result shows that IMI can indeed predict the link of observed locations. Despite the predictions is imperfect, it can already be a salient tool for the network deployment. We also apply IMI into 2 case studies that target to maximize the network coverage and also maximize the network robustness under random human movement blockage. So the left figure shows that by judiciously searching for the best AP placements, it can improve the network capacity by multifold compared to simply deploying the AP to the corner of the room or randomly choose a random locations of the room. And the right figure shows the link capacity reduction under random human blockage. And we found the IMI only suffer from, on average, we found the IMI only suffer from about 100 megabps bit rate drop. And the other two approach typically suffer from 600 to 800 megabps throughput drop. To conclude my talk, in this work, we propose IMI. It's a sensing assist design that's trying to facilitate the 60 GHz network deployment. So it represents a computational approach to radio environment reconstructions and network performance predictions. And we propose several processing algorithms that are able to disentangle different paths in the environment and reverse engineer the geometry of dominant reflectors. And through testbed experiments and case studies, we demonstrate how environment sensing can help augment the network planning and protocol reconfigurations. Thanks for your attention. I'm happy to take any questions.
Introduce yourself.
Mighty. Thanks for a very good talk. I have one question. What happens when they're moving reflectors in the environment when you're calibrating?
The moving reflector?
Yeah.
Actually, in here, we are trying to model a static environment. So memory is also the static reflector, like the wall and the cabinet.
What if there's like a humans walking around?
No, for the human, actually, it's typically in such a network, it's mainly modeled as an absorber rather than a reflector, because its blockage will mainly absorb the majority of signals of the 66 signal rather than reflect the signals around. Yeah. So for the human body's memory is a blockage or absorber rather than a reflector.
Yeah, thank you. So I have one more question. So you said you estimate the length of the paths.
Right.
How do you calibrate for the phase offset between the transmitter and the receiver? There is like a random phase offset.
We omit one detail in the talk. Actually, in the paper we discussed, at the very beginning, we need to do an initial calibration. We first need to place the radio at a known distance. And then, for example, the TSIs, they are separated by about 1 meter. And then we use the line of sight path as a reference. First, need to calibrate the initial phase difference. After that, we run the system.
Okay, thank you.
Cool. Any other questions?
Thank you. I'm Han Xu from Huawei. It is really an amazing work. It helped us to learn the surrounding reflector.
Right.
But I'm curious about that. It seems like your system have to work in an omnidirectional
Uh,
style, right? Both
you
the
mean
transmitter and receiver.
the phase array need to like cover the whole space?
Yeah.
The signals?
But I'm wondering, like in practice, some protocol like Wi-Fi AD and AY in processing, it seems that we are more focused on beamforming style in practice. How can your system help the practical applications?
You mean the beamforming
Yeah.
style?
Yeah.
I think in 60 years is different from the traditional like 2.4 or 5 years beamforming. So it's using a code book, and then their focus is energy, like form a narrow beam towards certain directions. So it's also not omnidirectional. It's also like, as mentioned at the beginning of the slide, it's still using a directional communications and form narrow beam toward the receiving device.
Okay, but it seems that you have to transmit the signal in a really wide angle, right?
No, so we will like try to transmit toward different directions, but for each direction the beam is narrow.
Okay.
Yeah.
So a related question, how long does it take to do the calculation?
Yeah, so currently, because we are running using a mooring antenna, mechanical mooring antenna, so it takes very long time. But it's better if using a commercial phase array that's electrically steerable. And then the time it takes is very short because each sampling it just takes less than 100 milliseconds. If you measure multiple times, at most it takes 1 second, like that. Yeah.
Yeah, I'm Yanzi from UCSB. So interesting work. I'm just curious how many locations you need to fully reconstruct the environment. I mean, how do you make sure the environment is enough? I mean, the reconstructed environment is enough for you to predict the signals.
Right. So that's a very good question. So in the paper, we have evaluation. Actually, this number it depends on the complexity of the environment. For example, if you just have like 2 reflectors, you use 10 locations is enough. Like in our evaluation, it has like 5 or 6 reflectors, and then it will take 15 to 20. And then for even more complex environments that have more, and then we found the numbers are still going up. That part of experience is through simulation, so the scalability. But in practice, owing to the 60-channel sparsity, the number of dominant reflector in a practical environment won't be too much. Mostly it will be the wall or some metal cabinet there. So we believe it won't take too much effort to like sense the environment.
All right, thanks.
So just to give the audience a ballpark number, for this kind of a room, what would you expect?
I think this kind of room is too large for the second room because typically it only can cover like 10
You'll
meters.
put multiple EPs, I would think.
Yeah, if we have multiple, but this room is really simple, like it have only 4 walls. So I think we plus some human intelligence, like if we intentionally sense near the wall areas, and then it's also just take like 10 to 20th of sampling locations.
So
to
your
recover
answer
the
is
room.
you just go around the walls, and that would
Yeah.
be the measurement.
Yeah.
Cool. Thank you. Let's thank the
Thanks.
speaker.